All right, welcome to The Explainer. Today we're going to take a journey, and I mean a real journey, down to the absolute smallest scale of reality. Why? To get a handle on the basic building block of our entire universe, the atom.
So let's just start with a huge question, right? What are you really made of? I mean, what's the fundamental stuff that makes up everything you see, everything you touch, even you? Imagine you could just zoom in, way past your skin, past your cells. What would you find at the very, very bottom of it all?
For literally centuries, people thought the answer was pretty simple. They figured it was just this tiny, solid, unbreakable little ball they called an atom. But oh man, they were wrong. The real story of the atom isn't about one single aha moment. It's more like a thrilling detective story, one that revealed the universe is just so much stranger and way more interesting than anyone could have ever guessed.
Okay, our detective story really kicks off in the late 19th century, and it starts with a total bombshell of a discovery, the atom. It wasn't the end of the line. It wasn't the smallest thing. It was actually just a container for even smaller, even more fundamental little pieces.
And it was through a whole series of just brilliant experiments by guys like J.J. Thomson, Goldstein, and Chadwick that we finally uncovered the three key players hiding inside every single atom in the universe. And these particles, they're the ones that define everything, like what an element is and exactly how it's going to behave.
Okay, so this table right here, it basically lays out our whole cast of characters. First up, you've got the electron. It's super lightweight and has a negative charge. Then there's the proton, which has the opposite, positive charge. And finally, the neutron, which, you guessed it, is neutral, no charge at all. But here's the kicker. Look at that mass column. The proton and the neutron are almost 2,000 times heavier than the electron. That might seem like a tiny detail, but trust me, it's going to be a huge deal later on.
So now we know the particles are there. The next big mystery was, how are they all arranged? Like, how do they fit together inside the atom? This puzzle led to some of the very first scientific models of what an atom might actually look like.
So, J.J. Thomson, remember him? The guy who discovered the electron? He was the first to take a real crack at it. He came up with what we call the plum pudding model. He basically pictured the atom as this kind of, a sphere of positive pudding with the tiny negative electrons just scattered throughout it, kind of like raisins or plums. Now, it was a pretty good first guess, you got to give him that. But this model, it had a fatal flaw. See, it assumed that all the positive charge and all the mass was just spread out evenly. And because of that, it just couldn't explain the results of this totally groundbreaking experiment by another scientist, Ernest Rutherford, who decided to fire a beam of tiny particles at a super thin sheet of gold foil. Okay, check this out. If that plum pudding model was right, all of those particles should have just zipped right through the foil like shooting bullets through a cloud of mist. And, most of them did. And this is the crazy part. A tiny, tiny fraction of them were deflected at huge angles. Some even bounced straight back. Rutherford later said it was as incredible as if you fired a 15-inch cannonball at a piece of tissue paper and it came back and hit you. I mean, wow.
That completely shocking result forced Rutherford to come up with a radical new picture of the atom. He realized the only way those particles could bounce back like that is if they were hitting something incredibly small, incredibly dense, and positively charged. So he proposed that the atom must be mostly empty space, and that all of its positive charge and almost all of its mass was packed into this tiny little center. He called it the nucleus, with the electrons orbiting around it, almost like planets circling the sun. And this wasn't just some abstract idea, right? Discovering that dense nucleus is what paved the way for everything from nuclear energy to modern particle physics.
But Rutherford's brilliant model created a brand new, completely baffling problem. See, according to the classic laws of physics at the time, an electron orbiting like that should be constantly giving off energy. And if it's losing energy, it should slow down and spiral right into the nucleus in like a fraction of a second. So his model predicted an atom that should basically collapse on itself instantly. But obviously, they don't. The world around us is stable. Something was seriously wrong with the physics. But what?
So, to solve the puzzle of the collapsing atom, we needed a new hero. Enter Niels Bohr, who brought this totally bizarre and revolutionary new idea into the world of physics, the quantum. Bohr came up with this really strange but incredibly powerful solution. He said, what if electrons aren't actually free to orbit just anywhere they want? What if they're locked into specific allowed energy levels, kind of like train cars stuck on fixed tracks? He suggested that as long as an electron stays in one of these special orbits, it just doesn't radiate any energy, and that's what prevents it from spiraling to its doom.
And this was a huge leap forward. I mean, Bohr's model worked perfectly for this simple hydrogen atom, but it was still an incomplete picture. It couldn't really explain the behavior of more complex atoms, and it couldn't account for those unique patterns of light, the atomic spectra, that different elements give off. The story was definitely not over yet.
Right. So the final pieces of this puzzle would end up shattering our everyday understanding of reality. To truly get a handle on the atom, we had to accept that at the subatomic level, the rules of the universe are just fundamentally different from the ones we see and experience every day.
And here's the absolute crucial point. The predictable, clockwork rules that tell us how a baseball flies or how a planet orbits, they just completely break down when you're talking about something as small as an electron. We needed a whole new rulebook, quantum mechanics. And this new science says that on this tiny, tiny scale, things get, well, fuzzy. You literally can't know both exactly where an electron is and where it's going at the same time. The very act of measuring one makes the other one uncertain. It's wild. So this leads us to a pretty mind-bending conclusion. An electron doesn't have a neat, planet-like orbit at all. No. Instead, it exists in this fuzzy probability cloud that we call an orbital. Now, this orbital doesn't show you the path of the electron, it just shows you the region of space where the electron is most likely to be found at any given moment. It's a fundamental shift from "this is where it is" to "this is where it probably is."
So, if we can't even know exactly where an electron is, how in the world do we build atoms and molecules and, everything? Well, the answer lies in a set of surprisingly elegant quantum rules that govern exactly how these probability clouds organize themselves around the nucleus.
Okay, rule number 1 is the Elf-Bow principle, which is just a fancy way of saying building up. You can think of this as the lazy tenant rule. Electrons are lazy. They will always take the easiest, lowest energy spot they can find. So as you see here, they fill up the orbitals in a very specific order, starting from the lowest energy level and then just building their way up, layer by layer.
Next up, we have the Pauli exclusion principle. This one acts kind of like a cosmic two-per-room rule. It basically says no two electrons in an atom can be exactly the same. What this means in practice is that any single orbital can hold, at most, 2 electrons. And if it does hold 2, they have to have opposite spins. You can sort of picture one spinning clockwise and the other spinning counterclockwise. And finally, there's Hund's rule. This is my favorite one. You can think of it as the bus seat rule. You know how when you get on a mostly empty bus, you take an empty row of seats for yourself before you sit right next to a stranger? Well, electrons do the same thing. When they're filling a set of orbitals that all have the same energy, they will each take an empty orbital first before they start pairing up.
And here it is. This is the big payoff. Just think about it for a second. These 3 kind of strange quantum rules, they're the foundation for all of chemistry. Seriously. They dictate the entire structure of the periodic table, they explain why some elements are super reactive and others are totally inert, and they govern exactly how atoms bond together to create literally everything in our world.
So, our little journey has taken us from thinking of an atom as a solid ball, to a tiny solar system, and now to this ghostly cloud of probability. We now know that you, me, and this desk you're sitting at are all made of atoms that are more than 99.9% empty space. So here's a final thought to leave you with. The next time you tap your hand on that desk, why does it feel solid? The answer is amazing. It isn't matter touching matter. It's the strange, repulsive quantum forces pushing back between those electron clouds.